Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to discuss the wonderful subject of calculus. We're going to go through an introduction to calculus, the major concepts, the major ideas behind it, what we can achieve with it. This is written for A-level students in the UK, Baccalaureate students overseas and in the UK, advanced GCSE students, scientists, and just anybody who's at home during lockdown and wants some entertainment and wants some fun. Maybe it's a date night at home. Let me know down below in the comments why you watched this, what you got out of it, and what you'd like to see in future. So firstly, what does calculus allow us to do? What is the point of it? It allows us to understand change and the rate at which quantities change. It allows us to calculate the area and volume of a very broad range of shapes and objects. So we can calculate the area of a square or a circle or a triangle, but calculus allows us to calculate the area and volume of a really broad range of shapes and objects. Why do I care? Why does anybody care? Well, it's essential. It's essential to physics. So speed is the rate of change of distance, acceleration is the rate of change of speed. The guys in Elon Musk's team and SpaceX will be doing calculus all the time, working out the rate of change of mass on the rockets as the fuel comes out of the back. Isaac Newton developed calculus as a way to solve problems that he was coming across in physics. By the way, while he was hiding from the Great Plague, in quarantine, ironically, he developed calculus as a way to address problems in physics. Biology, so births minus deaths gives us the rate of change of the size of different animal and human populations. Very important for ecology, diversity of species. In chemistry, rate of reaction might depend on the presence of a catalyst. In economics, growth rate is the rate of change of economic activity. So right now, growth is negative because we're locked down. But in future, as the wonderful inoculation moves through the population, vaccine moves through the population, the economy will open up again, growth will increase, and actually the vaccine could not have been developed without calculus. So it's helpful to anything which changes. There's a great song in Frozen 2, some things never change, and so those things don't need calculus, but for everything else, calculus is helpful. We love Frozen. Anyway, how does calculus do this? It does it by doing mathematics with very small quantities. So how small? Well, some people like to talk about limits. The idea of a quantity that gets arbitrarily close to zero but may not quite get there, doesn't quite get there. Others talk about infinitesimals, which are quantities that are smaller than any other number, in the same way that infinity is bigger than every other number. But either way, we're talking about tiny numbers, almost the smallest numbers we can imagine. To understand this fully, we need the idea of a function. So we say that y is a function of x when the number y depends on the number x. So for instance, the height of a child depends on the child's age. As a child gets older, he or she gets taller. We can record their height at different ages in months or in years and then plot a chart which we can put on the wall. This expresses height as a function of age. The speed of a train is a function of time. So it starts off stopped in the station. We can then plot the speed for each minute. I assume it would rise to a kind of cruising speed or a maximum speed and then fall as the train comes into the next station or hits a signal. So we can plot speed as a function of time. Profits of a company might be a function of its sales. So we don't always need to have time as a variable. It's just a way of connecting two variables. Price of oranges depends on the size of the orange crop. The bigger the crop, the lower the price, by the laws of supply and demand. A bit of free economics there. Anyway, when y depends on x, we write y equals f of x and say y is a function of x. But we could also say y is g of x, and then f and g would just be different functions that connect y and x. So we can have different letters for different functions, just as we have different letters for different numbers in algebra. So here, we're going to look at y equals f of x, where f of x is x squared. So this is a parabola. And we're going to imagine that this is a goods train carrying something very fragile, because we'll find out it's going quite slowly. It might also be a passenger train carrying some people who are fascinated by the scenery, but either way, it's a slow train. So y is distance in kilometres, x is time in hours. So question 1, what is the speed? So speed equals distance over time. So we can say, well, we travelled 100 kilometres, that's the y-axis, in 10 hours, that's the x-axis. So the speed is 100 over 10, 10 kilometres per hour. This is the average for the whole period. So I'm illustrating this graphically. So this straight line is the trajectory that the train would have taken if it travelled at a constant 10 kilometres per hour. Actually, that's very hard to do because that would entail acceleration from 0 to 10 instantaneously in the beginning, which you can't do. But just for illustrations, this is what it would look like. And we can work out the gradient of that straight line. The gradient is the change in y divided by the change in x, which is 100 over 10, which is 10. Now we can think about shorter time periods. So let's think about each hour on its own. So in the first hour, the train travels a kilometre in an hour, 1 kilometre per hour. In the second, it goes from 1 kilometre to 4, so it travels 3 kilometres in an hour, 3 kilometres per hour. And then in the 10th hour, it travels from 81 kilometres to 100, so 19 kilometres in an hour, 19 kilometres per hour. Here I'm just illustrating the gradient between hour 2 and hour 3. So we've gone from 4 to 9 kilometres, we've travelled 5 kilometres in an hour, 5 kilometres per hour. Now we can also dig down into shorter time periods. So this is going from 3.5 hours to 3.6 hours, 3.6 to 3.7. So if we go from 3.5 to 3.6, we can calculate that we travel 0.71 of a kilometre in 0.1 of an hour, which is 7.1 kilometres per hour. And we can see the speed slowly rising as we go through these short time periods. Now the idea behind calculus is to say we're going to go to a tiny time period and we're going to call it delta x or dx. And this allows us to work out a formula for the rate of change or the speed at any point in the journey. So if f of x equals x squared, we calculate something called the derivative, which is 2x. So if f of x is x squared, the derivative is 2x. We can also write it in a different notation. If y equals x squared, then we call the derivative dy by dx. Again, it's 2x. This is the exact speed at any point in the journey. So when x is 4, dy by dx is 2 times 4, which is 8. And if we look back at the previous grid, that makes perfect sense, because from 3.9 to 4, it was 7.9 the speed. From 4 to 4.1, the speed was 8.1. So it would make perfect sense that when x is 4, the speed would be 8. But using this derivative, we can work out the speed at any point. So when x is 2, the speed is 4. When x is 0, right in the beginning, the speed is 2 times 0, which is 0. When x is 10, the speed is 2 times 10, which is 20. When x is 3.5, the speed is 2 times 3.5, which is 7. Okay, so that's the fundamental ideas behind change and derivative. Now we're going to look at area. So we're going to look at the area under the curve y equals x squared. And we're going to estimate this by drawing a bunch of rectangles. So all of these rectangles are bigger than the area under the curve. So they're all like an envelope for the area under the curve. So we've got a rectangle between 9 and 10, which is 100 high. We've got a rectangle between 8 and 9, which is 81 high. All of these rectangles cover the curve. We're going to add up their areas. So it's 1 plus 4 plus 9 plus 16 plus 25 plus 36 up to plus 100 gives 385 is the area of all those rectangles put together. And that's going to be more than the area of the under the curve because it covers the curve. It covers the area under the curve. Now we're going to look at rectangles that fall below the curve. So the one between 9 and 10 is now 81 units tall, so it just touches the curve. The one between 8 and 9 is 64 units tall, so it just touches the curve. And so the area of these rectangles is 1 plus 4 plus 9 plus 16 plus 25 plus 36 up to plus 81, 285 units. So we've got two estimates. 385 is above, 285 is below. The actual area must be somewhere in between. Now again, basically what we're going to do is to take the width of those rectangles and assume it's a tiny number called delta x or dx. And then we will use calculus to work out a formula for the exact area underneath the curve between any 2 points. So firstly, we calculate something called the indefinite integral. Now I'll explain this in later videos. So for now, take it on trust. I mean, generally don't take things I say on trust. You should ask me to prove them. But for now, we'll take this on trust and we'll prove and derive it in later videos. So if y equals x squared, the indefinite integral is x cubed over 3. And we can now use that to calculate the area between the lines 0 on the left and 10, x equals 10 on the right. So we do that by substituting 10 into the indefinite integral. So 10 cubed is 1,000, divided by 3 is 333 and a third. Try saying that 5 times fast after you've just drunk some water, actually, while you're drinking some water. Minus, substituting naught, naught cubed is naught, divided by 3 is still naught, so it's 333 and a third minus naught, which is 333 and a third. But just a bit more illustration. We're going to calculate the area between the line x equals 3 and x equals 10. So here we do have something to subtract. So we put in x equals 10, which gives us 1,000 over 3, because 10 cubed is 1,000. Then we put in x equals 3, so 3 cubed is 27, divided by 3 is 9. So we've got 333 and a third minus 9, which is 324 and a third. So that would be the area between x equals 3 and x equals 10. Just a quick check back. We got 333 and a third as the area. If we look at these two, 385 was above, 285 was below, and so we'd expect the area to be somewhere in between. Well, the average of 385 and 285 is 335. So the average is pretty close to 333 and a third, and there's no reason it should be the exact average, but it shows that this feels right naturally. Okay, so that's all interesting, but you may also ask, what's the link between the derivative and the integral? So derivative and integral are two big ideas in calculus. How are they connected? Well, I'm glad you asked me that. They're inverse operations. So if we add 4 and take 4 away, we get back to the same number. So 9 plus 4 is 13. Take 4 is back to 9. If we multiply by 10 and then divide by 10, we get the same number. So 6 times 10 is 60, divide by 10 is 6, back to the same number. If you integrate a function and you then differentiate, you get the same function. It takes you back to the same function. So we're going to illustrate this. So now let's think about the area under the curve. So this curve we're going to call f of x. Let's think about the area under the curve, which is the integral. Now we're going to think about the rate of change of that integral. So we're going to think about the derivative of that integral. Well, this white rectangle right on the right hand side, this is a tiny thin rectangle. This shows how quickly the area is changing. It represents the rate of change, because the bigger it is, the more the area is changing as we increase x. So this signifies the rate of change of the integral, or the derivative of the integral, and as we can see, the size of the rectangle is literally just f of x. So that shows us that f of x is the derivative of the integral of x, which basically shows why the two of them are inverse to each other, why basically when you do one, you reverse the action of the other. I really hope you like this video. If you do, please feel free to press the like button, or even if you sort of slightly hated it, just press like anyway. Please subscribe in the future. We will send you more in the future. If you hit the notification bell, it will let you know. Most of all, I hope you enjoy your mathematics, and I really look forward to seeing you next time. Thank you so much for watching. See you next time.